Welcome to the deep dive. Today, we're plunging into, well, the fascinating world of artificial intelligence. It's everywhere, isn't it? Constantly changing.
Absolutely. And it's a topic that grabs headlines, but understanding what's really going on,
Mm-hmm.
that's trickier.
Exactly. So, a listener shared this really insightful book with us. It takes a good, hard look at where AI actually stands right now. What it can do, where it still kind of stumbles, and what the future might hold.
Mm-hmm.
So if you're keen to get the real deal on AI, maybe without getting totally bogged down in super technical jargon or just wild speculation.
Then you're definitely in the right place.
Yeah, we're hoping this deep dive acts as a bit of a shortcut for you.
Right. Our mission today is basically to pull out the most important bits of knowledge from this book. We'll look at the big wins, sure, but also some surprising limitations.
And try to clarify those big questions swirling around AI development, all based on the research in this source material.
Exactly. Solid grounding.
Okay, so the book kicks things off with this almost comical scene. The author's going to Googleplex for an AI discussion,
Uh-huh.
and he gets completely lost inside the Google Maps building.
You can't make it up, can you? The irony is just perfect.
Right. It immediately sets up this contrast.
It really does. You've got Google, this absolute powerhouse, pouring billions into AI, hiring Ray Kurzweil, buying DeepMind.
Their goal is literally solving intelligence. Huge ambition.
Huge. And yet, navigating their own building relies on the very tech being discussed. It kind of highlights the complexity of it all.
It really does. And Google's commitment is undeniable, right? Kurzweil, all those AI startups, they snap up.
Definitely. But the book makes a really crucial point early on. The AI field itself isn't singing from the same hymn sheet. There are some pretty deep divisions.
Okay, like what?
Well, you've got wildly different perspectives. Some experts genuinely think we're, right on the cusp of true AI, artificial general intelligence.
Like any day now, sort of. While others are saying, whoa, hold on, that's centuries away, if ever. And the same goes for outcomes total utopia versus, dystopian nightmares. It's a huge spectrum.
So the book tries to cut through that noise.
Exactly. The author isn't aiming for a general history lesson. It's focused on the AI methods that are actually impacting our lives right now, today.
And challenging how we even think about what intelligence means.
Precisely. It digs into the techniques driving things now, and that forces us to ask these fundamental questions, which is a good place to start understanding how these systems actually work.
Okay, so how do they work? The book brings up this early kind of philosophical split. Symbolic versus sub-symbolic AI. What's the deal there?
Right. So back in the early days, AI research basically went down two main paths. Symbolic AI was the big one for quite a while.
That sounds logical.
It was. It focused on building systems based on explicit rules and logic. Think of programs like the General Problem Solver. It used logical steps to solve puzzles.
Or expert systems like MYCIN back in the day, which tried to diagnose diseases using rules gathered from doctors.
So manipulating symbols according to rules, if this, then that.
Exactly. But here's the kicker, the point the book makes. Did the computer understand those symbols?
Probably not.
Right. It could process fever and cough, according to the rules, but it had no idea what a fever feels like or what coughing is. You could swap them for nonsense words.
And it would run the same.
Precisely. It lacked semantic grounding. No real connection to the meaning behind the symbol.
Okay, got it. Just symbol shuffling. So what was the other path, the sub-symbolic one?
That approach looks somewhere else entirely for inspiration. The brain.
The biological route.
Exactly. A key figure here was Frank Rosenblatt back in the late 50s with his perceptron.
Perceptron sounds futuristic.
It was, for its time. It was basically an attempt to create a simplified mathematical model of a biological neuron.
Okay, walk me through the simple version. How does a neuron work, and how did the perceptron copy it?
Well, super simplified. A neuron gets signals from other neurons through connections. These connections aren't all equal. Some are stronger than others think weights.
Okay, weights?
The neuron adds up these weighted signals. If the total hits a certain level, a threshold.
It fires, sends its own signal.
Bang on. Rosenblatt's perceptron was a digital version. It took numerical inputs, each multiplied by a weight, summed them up, and checked against a threshold to produce an output.
And the idea was that it could learn. That sounds like a big difference from the fixed rules of symbolic AI.
Huge difference. That was the key idea. Instead of programming rules in, the perceptron's knowledge was in those weights and the threshold.
So how did it learn? How did it adjust the weights?
Rosenblatt proposed learning from examples. You show it an input, it makes a guess. You tell it if it's right or wrong.
Feedback.
Exactly. This evolved into what we call supervised learning. Based on the feedback, how wrong it was, it would slightly adjust its weights and threshold.
Trying to do better next time.
Precisely. Trying to minimize the error over lots and lots of examples.
But this brain-inspired approach, it didn't just conquer the world immediately, did it? The book mentions an AI winter. Sounds chilly.
It was. The initial burst of enthusiasm for both symbolic and these early connectionist ideas started to fade. Symbolic AI especially had promised a lot, understanding language, common sense.
And it didn't deliver.
Not on the scale people expected by the mid-70s. So funding agencies, the governments in the UK and US, they got skeptical. Budgets were slashed.
Ouch! Hence the winter.
Yeah, a period of much lower funding and, frankly, lower expectations. It affected both approaches.
But the sub-symbolic, the connectionist idea, it didn't just vanish, right? It made a comeback.
That's right. People who believed in connectionism, this idea of brain-inspired architectures that learned from data they kept plugging away.
Like Rumelhart and McClellan.
Exactly. Their work showed enough promise that interest started picking up again, especially from places like DARPA.
DARPA, the U.S. Defense Research Agency.
Yeah. And there's this quote from a DARPA official around 1988 saying neural networks could be more important than the atom bomb.
Wow. That's quite a statement.
It signaled a big shift. Funding started flowing back, enthusiasm returned, paved the way for what came next.
Which brings us to machine learning and specifically deep learning. Now, the book clarifies that word deep. It's not about, like, profound thoughts.
Not necessarily. It's a really important clarification. Deep in deep learning refers to the structure of the neural networks.
How many layers they have.
Exactly. Deep learning models have multiple layers, more than one hidden layer between the input and output. It's about architectural depth, not necessarily conceptual depth.
Okay, good distinction. Deep learning is a type of machine learning, which is a part of AI.
You got it. It's one set of powerful techniques within that broader field.
Right. Now, switching gears slightly, the book talks about a classic AI benchmark, the Turing test. Still relevant.
Well, it's certainly iconic. Alan Turing proposed it way back in 1950, remember? Can a machine fool a human into thinking it's also human in a text conversation?
The imitation game.
That's the one. If the judge can't reliably tell the difference, the machine passes.
And the book mentions this chatbot, Eugene Guzman, supposedly passed it in 2014, but there was controversy.
Yeah, big controversy. It fooled a percentage of judges in these short 5-minute chats. But critics jumped on it.
Why?
They argued the test wasn't very strict, the conversations were too short, and crucially, the chatbot pretended to be a 13-year-old Ukrainian kid.
Ah, a built-in excuse for grammatical errors or not knowing things.
Exactly. It made it easier to seem plausibly human, perhaps artificially so. So past was a strong word for some.
Context matters. Okay, this leads us to Ray Kurzweil again and his very optimistic predictions. Turing test by 2029, the singularity.
Kurzweil's famous for these predictions. He sees AI passing a more robust Turing test by 2029, and then the singularity to this point where AI surpasses human intelligence, triggering runaway technological growth around 2045.
And he bases this on exponential progress.
Yeah, the power of exponential growth, like Moore's law for computer chips.
The book uses the rice on a chessboard analogy, right? Explain that quickly.
Classic example. 1 grain on the first square, 2 on the second, 4 on the third, doubling each time.
Start slow.
Very slow. But by the time you're halfway across the board, the numbers are astronomical. Exponential growth sneaks up on you, then explodes.
And Moore's law chips getting denser and faster exponentially has fueled AI. Kurzweil thinks this continues.
He does. He believes this relentless exponential trend in computing and other tech will inevitably lead to those breakthroughs he predicts.
But not everyone buys it. The book mentions a bet between Kurzweil and Mitchell Kapoor.
Right, a long bet ending in 2029 on whether an AI can pass a much stricter Turing test. And they had very different ideas about what that really takes.
Kapoor's view.
Kapoor argued that real human understanding comes from having a body, from interacting with the physical world, from lived experience. He thinks a lot of our knowledge, especially common sense and emotional understanding, is tacit. It's not written down anywhere.
So you can't just program it in or learn it from text.
That's his argument. Without that embodiment and experiential learning, he doubts an AI could ever truly pass a demanding test of human-like intelligence.
And Kurzweil's counter.
Kurzweil thinks, well, by the 2030s, virtual reality will be so immersive that AI can have simulated physical experiences, and he expects we'll have reverse-engineered the brain enough to build AI with emotions.
So a virtual body and simulated emotions.
Essentially, yeah, a fascinating disagreement about the fundamental nature of intelligence.
Definitely. Okay, let's shift focus now to where deep learning has had massive success. Computer vision, recognizing objects. The 2010s were apparently a huge leap forward.
Oh, absolutely transformative.
Primarily
Driven by deep learning and specifically convolutional neural networks, ConNets.
cone nets, inspired by our own vision system.
Very much so. Our visual cortex has layers that process information hierarchically. ConNets mimic that structure.
How? Layers of artificial neurons.
Yep, layers of simulated neurons or units. Each layer takes input from the previous one, and the units act like feature detectors, looking for specific patterns in small regions of the image. They create these activation maps.
So early layers look for simple stuff, like lines and edges.
Exactly, like Hobel and Wiesel found in cat brains decades ago. Early ConNet layers detect edges, corners.
And deeper layers combine those to find more complex shapes.
Precisely. Combinations of edges become corners or textures. Deeper layers recognize parts of objects and eventually whole objects. It's a hierarchy of increasing abstraction.
Cool. But to learn all this, they needed data. Lots of it. Enter ImageNet.
ImageNet was absolutely crucial. Before that, datasets were too small, too limited. Fei-Fei Li at Princeton had this vision.
To create a massive labeled image dataset.
Yes. Using WordNet, this big database of English words as a framework, and then getting humans to label millions of images.
And she used Amazon's Mechanical Turk for the labeling.
She did. Which is kind of ironic, isn't it? Using human intelligence to create the data to train artificial intelligence. It perfectly illustrates Marvin Minsky's point about easy things are hard.
Easy for humans, hard for AI at the time, like recognizing objects.
Exactly. Mechanical Turk provided the human power to label images at the scale needed.
And ImageNet led to the big breakthrough moment in 2012, AlexNet.
That was the turning point. The ImageNet competition was the proving ground. In 2012, AlexNet, a deep ConNet, developed by Alex Kurzhevsky and his team.
It just blew the competition away.
Pretty much. Its accuracy was significantly better than the traditional computer vision methods used before. It really showed the power of deep learning for this task.
And having more computing power helped train these bigger networks.
Definitely. GPU's graphics processing units turned out to be really good for the kind of math involved in training deep nets. That, plus the massive ImageNet dataset, was the perfect storm.
Success attracts attention. The tech industry got very interested.
Oh yeah, the ImageNet competition quickly went from academic exercise to high-stakes corporate race, which led to issues.
Like the data snooping incident the book mentions.
Right. Baidu, the Chinese tech giant, got caught essentially peeking at the test data to boost their scores in 2015.
Cheating, basically.
It violates the principle of the test set, yeah. It's meant to be unseen data to check if the model generalizes. It showed how intense the competition had become.
So, with these successes came claims of AI surpassing human-level performance on ImageNet. True.
Well, sort of, but with big caveats. The book urges caution here. Yes, some ConNets got error rates slightly lower than the reported human rate.
Okay.
But that human rate was based on one single highly trained expert, Andrej Karpathy, spending hours on the task. Not exactly representative of average human vision.
Ah, okay. And just recognizing objects in ImageNet isn't the same as human vision anyway, right?
Not even close. It's a very specific, constrained task. Human vision involves understanding relationships, actions, intentions, context, so much more. Object recognition is definitely not solved.
What are some key things current AI vision still struggles with?
Oh, lots. Understanding relationships between objects, the cat is on the mat, understanding actions, what someone is doing, inferring goals, emotions. These are still huge challenges.
This feels related to the long tail problem, especially for things like self-driving cars.
Exactly. The long tail is all those countless low-probability weird situations you might encounter. A deer jumping out, a weirdly placed traffic cone, unusual weather.
Stuff that happens rarely, but a self-driving car has to handle it.
Right. And humans often handle these novel situations using common sense, this vast web of background knowledge about how the physical and social world works.
Which current AI mostly lacks.
Pretty much entirely. We use it constantly, effortlessly. AI doesn't have that deep well of experience and knowledge to draw on for the unexpected.
So a human driver sees a mattress fall off a truck ahead. They use common sense to react, and AI might just freeze or do something unpredictable.
It's a major challenge. True autonomy seems to require something akin to common sense, and we're not there yet.
Which makes the next topic even more worrying. Adversarial attacks. What are these?
These are fascinating and quite concerning. Adversarial examples are images that are tweaked, just slightly, in ways a human probably wouldn't even notice,
Tiny changes.
often imperceptible. But these tiny changes can cause a state-of-the-art deep learning vision system to completely misclassify the image, often with very high confidence.
So it looks like a panda to us, but the AI confidently says it's a gibbon.
Exactly that kind of thing. It reveals a fundamental difference between how these systems see and how we do.
The book gives examples like special glasses fooling face recognition, or stickers making stop signs look like speed limit signs to an AI, even messing with medical images.
Yes, those are real examples.
Yeah.
It shows these systems can be brittle, vulnerable. Imagine the security risks, the safety implications.
It's scary, and it makes you wonder, what are these networks actually learning if they can be fooled so easily? Do they understand stop sign?
That's the million-dollar question, isn't it?
Yeah.
It strongly suggests they're learning statistical correlations in the pixels, shortcuts maybe, rather than the underlying concept in a robust, human-like way.
So AlexNet recognizing a school bus isn't because it knows what a school bus is functionally.
It's more likely learning visual patterns, yellow color, certain shapes, window patterns that are statistically associated with the school bus label in its training data. Adversarial attacks exploit the gaps in that pattern matching.
They lack understanding of 3D structure, object function, context, combining senses, all the stuff we do naturally.
Precisely. There's a huge gap between their pattern recognition and genuine, robust visual understanding.
Which leads nicely into what the book calls the great AI trade-off. Can you unpack that?
It's this core tension we're facing. AI offers amazing capabilities, huge potential benefits. We want to embrace that.
Well,
But we also know current AI makes weird errors, can be biased, is vulnerable to these attacks, and often operates like a black box. We don't fully understand why it makes the decisions it does.
so the trade-off is, how much do we trust it? How much control do we give it versus keeping humans in the loop?
Exactly. Where do we draw the line? Especially in high-stakes areas like medicine, finance, transport. How reliable does it need to be?
The book uses automated face recognition as a prime example of these ethical dilemmas.
Yeah, it's a perfect case study. Facebook system got surprisingly good at tagging photos.
Creepily good sometimes.
Right. But the technology raises huge red flags. Privacy, mass surveillance, potential for misuse by governments or police.
And bias, right. Systems working less well for certain demographic groups.
A major documented problem. Bias in the training data leads to biased performance, often disadvantaging women or people with darker skin tones. Serious fairness issues.
And some big tech companies, Amazon, IBM, Google, have actually pulled back or paused offering face recognition, citing these concerns.
They have. It shows even the creators are grappling with the ethical implications, which raises the next big question. Who regulated this stuff?
It can't just be the AI researchers or the companies themselves, surely.
The book argues strongly against that. These are societal issues, not just technical ones. We need broader input, governments, ethicists, the public, nonprofits.
Like the Partnership on AI, bringing different groups together.
Exactly. We need diverse perspectives to figure out the rules of the road for safe and ethical AI development and deployment.
And that ties into the value alignment problem, making sure AI goals align with human values. The book mentions the trolley problem.
Ah, the classic ethical thought experiment. How should a self-driving car choose in an unavoidable accident scenario? Swerve and hit one person, or stay the course and hit five?
No easy answer.
Absolutely not. And surveys show public opinion is divided and complex on how these moral choices should be programmed, if they even can be. It highlights the challenge of encoding human values into machines.
Okay, shifting gears again. The book moves into reinforcement learning, learning by trial and error. The robot Rosie kicking a ball.
Yeah, so it's a nice intuitive example. Reinforcement learning, RLE, is about an agent, Rosie, the robot, learning through interaction.
Yeah. Takes an action, gets a reward or punishment.
Exactly. Rosie tries kicking randomly at first. Most kicks miss, no reward. But maybe one kick connects, sends the ball forward, gets a reward.
Like training a dog with treats.
Very similar principle. Over many, many trials episodes, Rosie gradually learns which actions, in which situations, lead to rewards.
So it connects, ball is here, my foot is here, with kick like this.
Right. It learns a policy, a strategy for maximizing rewards over time.
The book mentions a Q table for keeping track of this.
Q learning is a common RL algorithm. The Q table is basically Rosie's memory of how good each action is in each state. Q stands for quality.
So for state ball is close and center, the Q value for action kicks straight hard gets higher if that leads to rewards.
Precisely. It learns the expected future reward for taking an action in a given state and updates this table based on experience. It's building its value map.
The book also mentions Arthur Samuel's checkers program from way back, an early RL
A
example.
landmark, really. Back in the 50s, it learned by playing against itself thousands of times.
How?
It used a game tree to look ahead at possible moves and an evaluation function to score how good a board position was. By dusting that function based on whether moves led to wins or losses, it got better and better, became a very strong player, showed the power of self-play learning early on.
Which naturally leads to Deep Blue versus Kasparov in chess.
A huge moment, 1997. Chess was seen as the pinnacle of human intellect by many AI pioneers.
So Deep Blue winning felt like a major milestone, crossing a threshold.
For many, yes. It used massive computing power and clever search algorithms, but it showed machines could beat the best human in this complex strategic domain.
But then came Go. Why was Go considered so much harder than chess for AI?
The sheer complexity. The number of possible moves at each step in Go, the branching factor, is vastly larger than in chess. Brute force search like Deep Blue used just wasn't feasible.
Too many possibilities to explore.
Way too many. So AlphaGo's victory over Lee Sedol in 2016 was stunning. Many thought Go was safe from AI for decades more.
And AlphaGo used deep learning, combined with other techniques.
Yes, specifically deep reinforcement learning. It combined deep neural networks, trained through self-play, with a sophisticated search technique called Monte Carlo tree search, a real breakthrough.
But even with these amazing game-playing feats, the book warns against anthropomorphism, right? Saying AlphaGo understood Go or discovered strategies.
Exactly. It's very tempting to use human terms, but we need to be careful. Gary Marcus, a well-known critic, argues these systems are learning incredibly specific correlations, not deep, flexible understanding.
Like the AI playing the breakout game, it mastered it. But if you move the paddle slightly, its performance collapsed.
That's a classic example he uses. It learned the exact contingencies of that specific setup, not a general concept of hitting a ball with a paddle. It shows the learning can be very narrow, very brittle.
Which highlights the massive gap between games and the real world, like a robot loading a dishwasher.
Completely different ballpark. Games have fixed rules, clear goals, limited states. The real world is messy, unpredictable, infinitely varied.
A dishwasher has different plates, bowls, weird shapes. Things might be wet, slippery.
Exactly. All the assumptions underlying AlphaGo perfect information, discrete turns, fixed rules are violated. Real-world robotics is vastly harder.
Okay, let's tackle AI and language. Natural language processing, NLP. The book starts with a simple story to show how tricky language is.
Ah, the restaurant story. Guy orders a rare hamburger, gets it burned, says, "Great job," sarcastically.
Easy for us to understand the sarcasm, hard for AI.
Very hard without common sense.
Yep.
You need to know about restaurants, ordering food, politeness, typical human reactions. All this background knowledge we just have.
So just processing the words great job isn't enough. You need context and world knowledge.
Absolutely. Which makes things like question answering really difficult. A child asking why repeatedly shows how much implicit knowledge underpins even simple statements.
Speech recognition, though the book calls it maybe AI's biggest success so far, thanks to deep learning.
It's been transformed, yes. Accuracy in quiet conditions is near human now for transcription. Dictation software, smart speakers, they work pretty well.
But still not perfect, still lacking understanding.
Right. They still struggle with noise, accents, multiple speakers. And the errors they do make often show a lack of meaning, mistaking homophones like moose and moose. They're transcribing sounds, not understanding concepts.
Okay, what about sentiment classification? Figuring out if a review is positive or negative.
Another NLP task. Seems easy for us, but tricky for AI due to nuance, sarcasm, complex sentences.
Early systems just counted positive or negative words.
Yeah, which is easily fooled. This movie wasn't bad, contains bad, but is positive. You need more sophistication.
This leads to word vectors or embeddings trying to capture meaning numerically.
Exactly. The idea is to represent words as points in a high-dimensional space, where words used in similar contexts are closer together.
Like dog and cat might be near each other and maybe near pet.
Kind of, yeah. Techniques like Word2Vec learn these representations from massive text data sets. They capture some relationships, like analogies, king is to queen as man is to woman.
Mathematically.
Yeah, through vector arithmetic. It's clever. But it's not full understanding. And these vectors can inherit biases from the text data.
Like associating doctor more with man and nurse more with woman.
Unfortunately, yes. That's a well-documented issue. Bias in, bias out.
Machine translation, Google Translate, etc., also revolutionized by neural networks.
Big time. We move from older statistical methods to neural machine translation, NMT. Uses decoder architectures, often with things like LSTMs.
In technical terms, but basically neural nets reading the input sentence and generating the output sentence.
That's the gist. And the quality jumps significantly. Much more fluent translations.
But still not perfect. Claims of human parity were maybe exaggerated.
Generally, yes. While NMT is amazing, it still makes subtle errors, loses nuance, mistranslates idioms, fails on complex sentences sometimes. The book's example of back-translating the restaurant story shows how meaning can get mangled.
And image captioning AI describing photos? Similar story. Impressive but brittle.
Very similar.
Yeah.
Uses related deep learning techniques, can generate captions like a dog catching a frisbee in a park, sometimes spot on,
And sometimes,
sometimes wildly wrong. A group of elephants flying through the air. It hallucinates things or misinterprets the scene completely. Again, pattern matching without deep understanding.
okay, last NLP area. Question answering. IBM's Watson on Jeopardy! Was that true AI?
Big debate there. Watson was an amazing engineering feat, no doubt. It processed the questions, searched vast databases incredibly fast, ranked potential answers.
But was it understanding the question like a human?
Many critics argue no. It was more about sophisticated information retrieval and pattern matching against its knowledge base. IBM's later attempts to apply Watson in healthcare, for instance, had very mixed results, didn't live up to the hype.
And newer benchmarks, like SQUAD, Stanford Question Answering Dataset.
Squad tests systems on finding the answer span within a given paragraph. It's more about text extraction than true reading comprehension.
So it can find the sentence with the answer, but doesn't necessarily understand the paragraph as a whole.
Often, yes. It struggles with questions requiring reasoning across multiple sentences, understanding implications, or using world knowledge not explicitly in the text.
Newer tests are trying to push beyond that, asking questions that need common sense.
Yes, researchers are designing harder tests, like needing to know that you pour water into a cup, not the other way around, to resolve pronoun references correctly. Things that require basic world knowledge.
So the core message for language seems to be, you need common sense. Real-world knowledge is essential for human-level understanding.
That's the fundamental argument the book makes. Language is grounded in our experience of the world. Current NLP systems, impressive as they are, lack that grounding, making them inherently brittle.
So how do we get towards that deeper understanding? The book talks about knowledge, abstraction, analogy.
Right. If deep learning alone isn't enough for general intelligence, what's missing? One idea is structured knowledge.
Like the Psych Project, trying to manually encode common sense.
Exactly. A hugely ambitious, decades-long project to build a massive database of common sense facts and rules.
How's that gone?
It's ongoing. It's incredibly difficult. Capturing all the implicit, tacit knowledge humans have is a monumental challenge. And it's not clear if just having the facts is enough without the ability to reason flexibly with them.
Which brings in abstraction and analogy. The author seems really interested in this. Bongard problems.
Yes. Bongard problems are these visual puzzles. You see two sets of symbol diagrams, 6 on the left, 6 on the right. You have to figure out the abstract rule that distinguishes the left set from the right set.
Sounds tricky. Requires pattern spotting and abstract thinking.
Exactly. They often involve subtle concepts. And they're very hard for current AI.
And letter string analogies, like ABC is to abd as ek is to.
Ah, yeah. Another classic AI challenge, explored by Douglas Hofstadter with his copycat program. It tried to model the flexible, fluid way humans make analogies, including conceptual slippages.
Slippages.
Like realizing the rule might need to bend slightly to make the analogy work. Humans do this easily. Copycat tried, but human-level analogy remains elusive for AI.
And metacognition, thinking about your own thinking. AI lacks that too.
Largely, yes. Reflecting on your strategy, realizing you're stuck, trying a different approach that's key to human problem solving, and mostly missing in AI.
So the argument is maybe deep learning is hitting a barrier of meaning. It's great at pattern matching, but struggles with knowledge, abstraction, analogy, common sense.
That seems to be the book's central thesis, or at least a major theme. We need more than just bigger data sets and more layers. We need ways to imbue AI with these other crucial aspects of intelligence.
Andrej Karpathy's point about watching someone walk a dog, how much knowledge is needed to really understand that simple scene.
Yeah, Karpathy noted that even describing that scene fully requires understanding physics, biology, social conventions, intentions, 3D space, object permanence.
Yeah.
It's incredibly rich, far beyond current computer vision.
Which leads some to argue for embodiment. Robots interacting with the physical world as a path to intelligence.
It's an increasingly strong argument. Maybe intelligence needs a body and real-world interaction to develop common sense and grounded understanding, like Kapoor argued in his bet.
Okay, wrapping up. The book looks to the future, referencing Hofstadter's questions from Gödel, Escher, Bach. What kind of speculations come up?
Things like, will we get truly autonomous cars? Level 5. The book is skeptical, citing the long-tail problem as a huge hurdle, maybe level 4 in limited areas, but full autonomy everywhere seems distant.
What about AI creating art?
Another Hofstadter question. AI can generate images, music, but does it devalue human creativity? Does the AI understand aesthetics? The book suggests human appreciation and context are key.
It also reminds us that computers used to be humans doing calculations.
Right. A historical perspective. Electronic computers were initially superhuman only at arithmetic. Maybe AI is similar now, superhuman in narrow tasks, but far from generally intelligent.
And predictions for imminent general AI have repeatedly failed. The author sides with Kapoor's skepticism in the bet ending 2029.
Seems that way. The author emphasizes that the real near-term worry isn't runaway superintelligence.
But what?
The brittleness of current AI and our tendency to overtrust it because we anthropomorphize. We see intelligence where it's mostly pattern matching, and we deploy systems in critical roles without enough human oversight. That's the immediate danger.
Okay, so let's summarize the key takeaways from this deep dive. AI has made huge strides, right? Especially with deep learning in areas like image recognition, game playing.
Absolutely remarkable progress in specific domains, no question.
And it's a big but. It
Yeah.
still fundamentally lacks things like common sense, genuine understanding, abstraction, analogy, and robust handling of the unexpected.
That's the core message. Adversarial attacks show the brittleness, language processing shows the lack of grounding, game playing shows the narrowness. The gap to human intelligence remains vast.
Those aha moments, realizing the limitations behind the impressive demos, are crucial.
Definitely. It helps cut through the hype and gives you a more realistic picture of where we actually are. It's complex, it's moving fast, but it's not magic.
And hopefully this discussion has given you, the listener, a good framework for thinking about it all without feeling too overwhelmed.
Yeah, it's a lot, but hopefully digestible. Which leaves us with a final thought for you to chew on.
Given everything we've discussed, the power, but also the flaws, the biases, the vulnerabilities, the lack of deep understanding in current AI,
What are the really crucial considerations we need to keep front and center as this technology develops further? How do we ensure it's used for genuine human benefit while actively mitigating the risks and potential harms?
something to think about. What ethical guardrails, what kind of oversight, what societal conversations do we need to be having right now?
A critical question as AI becomes ever more integrated into our world.